Imagine this headline. Master in billiards and bridge, almost flunked physics, gets Nobel Prize. I mean, it sounds totally made up, right?
It really does. But it's the actual story of Ivar Giaever, who snagged a Nobel Prize in physics back in '73. Quite the hook.
Absolutely. And that's what we're diving into today, not just, the hardcore science, electron tunneling, superconductivity, that kind of thing.
Right, but also the journey behind it. It's very human, lots of twists, practical fixes, not exactly a straight line to discovery.
Yeah, it really shows how science actually happens sometimes. So our mission today is to get into quantum tunneling and superconductivity, but through Giaever's unique lens.
Exactly, and maybe get a feel for how scientific progress itself works along the way. It's a fascinating story.
Okay, let's jump in. So the man himself, Giaever, he really played down his own academic brilliance, didn't he?
Oh, completely. He openly said he almost failed physics and math back in Norway, Trondheim.
Right.
Said he just wasn't interested in mechanical engineering, or school in general, really.
Wow. So how did he even end up in physics?
Well, it's kind of a roundabout story. First, there was a housing shortage in Norway, believe it or not.
Seriously?
Yeah. So he moves to Canada in '52. And there, he takes this, 3-year company course. Engineering, applied math.
Okay.
And that's when it clicked. He said it made him realize school was for real. So he actually started hitting the books.
Ah, the practical motivation.
Yeah.
And then Schenectady, New York.
Right. Moves there when he's 28. And here's the kicker. He finds out physicists can actually earn a decent living.
Huh. That was the spark.
Apparently. He's an engineer, remember, but thought, okay, maybe I should learn physics. And he got this amazing chance at the General Electric Research Lab.
Incredible. But he was still coming at it from an engineering angle, right? What was his first assignment?
Thin films. And the funny part, which he loved telling, was that he thought films meant, photography film.
No way.
Yep. It just shows you where his head was at. Very practical, not theoretical at all.
But maybe that wasn't such a bad thing. You mentioned John Fisher.
Yeah, John Fisher. Crucial influence. Another mechanical engineer, but he'd pivoted into theoretical physics.
Okay.
And Fisher had this vision, really, that thin film technology could create genuinely useful electronic devices. That idea kind of set the direction for Giaever.
So it wasn't just pure theory driving it. It was this practical goal from another engineer turned physicist.
Exactly. It kind of challenges that stereotype of the lone genius theorist, doesn't it? Sometimes the breakthroughs come from, unexpected places, people with different backgrounds looking at things fresh.
Totally. Okay, let's shift gears a bit. Quantum tunneling. This is where things get weird. How do we even start to explain this?
Right. It's famously counterintuitive. The classic analogy helps, I think. Imagine throwing a tennis ball at a solid wall.
Okay, easy enough. It bounces back.
Always in our everyday world. That's classical physics. But quantum mechanics, which governs the tiny stuff, says something wild. It says that tennis ball, it actually has a chance, a tiny chance, but non-zero, of just passing straight through the wall. Tunneling.
Without breaking the wall or the ball.
Exactly. Now, for a tennis ball, the probability is so small we'd never, ever see it. It's effectively zero.
So, how does this become relevant for Giaever? You can't build devices with impossible tennis balls.
Right. The trick is scale. You need, as Giaever put it, very tiny balls, electrons, and lots of them.
Ah, okay. So the electrons are the balls. What's the wall?
So imagine you have two pieces of metal really close together. The electrons are inside the metal. The wall is the tiny gap between them, maybe a vacuum, or crucially, a very thin insulating layer.
Got it. But don't electrons need energy to jump across a gap?
Classically, yes. They don't have enough energy just to leap out of the metal into the vacuum or insulator. But quantum mechanics allows them to tunnel across that barrier if it's incredibly thin.
How thin are we talking?
Really thin. Around 100 angstroms, that's 10 billionths of a meter, roughly.
Wow. Okay. So classical physics for big stuff, quantum mechanics for tiny things like electrons, and that's what Giaever's trying to measure, this tunneling current.
Precisely. But getting there wasn't exactly smooth sailing. He and Fisher, remember, neither had a strong experimental physics background.
Right, the engineers.
So they had what Giaever called false starts. They'd see weird current voltage readings, these miracles, but then they couldn't reproduce them. Vanished.
Super frustrating, I bet. What was going wrong?
Well, a couple of things. Vibrations were a huge problem, messing up the tiny gap. And their early insulating layers often had tiny holes, little shorts, just inconsistent.
So how did they crack it?
The breakthrough was realizing they could use a naturally grown oxide layer. This was clever.
How did that work?
Okay, so the setup became evaporate a strip of aluminum onto a glass slide, then just expose it to plain old air for a little while, a few minutes maybe.
And that grows an oxide layer.
Exactly. A super thin, generally uniform, insulating layer of aluminum oxide forms naturally. Then you evaporate your second metal, say lead strips, across the first one.
Ah, so the oxide is the tunneling barrier, and it forms itself perfectly.
Pretty much. It solved the pinhole problem and was much more robust against vibrations. It was elegant, really.
When did they know it was really working? Was there a specific moment?
Yes. The key was getting the oxide thickness just right. He found that exposing the aluminum to air for only a few minutes created a layer maybe 30 angstroms thick.
Okay.
And that let him reliably measure the current versus voltage. He talked about that feeling, the anticipation right before you see if your experiment worked.
And this time?
It worked. He described being incredibly excited because the graph, the current voltage curve, dramatically changed when he cooled the lead down until it became superconducting.
So normal state, one graph. Superconducting state, a totally different graph.
Exactly. You can see it in Figure 7 from his lecture. He knew that was the aha moment. He immediately did it again on another sample, same result. Consistent.
That must have felt amazing.
Yeah.
But how did he confirm it was really tied to superconductivity?
Good question. The standard test is using a magnetic field. Superconductivity gets destroyed by strong enough magnetic field.
Right.
He didn't have the right low-temperature magnet set up himself. But luckily, right across the hall was Israel Jacobs, who specialized in low-temp magnetism.
Convenient.
Incredibly. Giaever just walked over, used Jacobs' rig, and bam, applied a magnetic field. The weird current voltage curve vanished, and it went back to the normal state curve.
Wow. Perfect confirmation. That's Figure 8, right?
That's the one. It showed conclusively that the effect was linked to the lead being superconducting. He was really fortunate to have that colleague and equipment right there. Quick validation.
So these experiments, they weren't just cool demonstrations of tunneling. They connected to something bigger, right? The BCS theory.
Absolutely central. His results provided the first really direct experimental evidence for the energy gap in a superconductor, which was a key prediction of the brand new Bardeen-Cooper-Schrieffer theory.
Okay, energy gap. Let's unpack that a bit. What does that mean in simple terms?
Basically, BCS theory said that in a superconductor, there's a range of energy levels that electrons just cannot have. It's like a forbidden zone. This gap is directly related to the electrons pairing up and moving without resistance. Giaever's tunneling experiments essentially let him measure the size of this forbidden energy gap. It was physical proof of this core theoretical concept.
That's huge. Was it immediately accepted?
Well, he said his friends were initially a bit skeptical about his interpretation, but importantly, they encouraged him to keep going.
That's good collegial support.
Definitely. And he wasn't shy about asking for help. He relied on theorists like Charles Bean and Walter Harrison to understand the expected size of this gap, just a few millielectron volts. Luckily, that translated to a voltage range his setup could actually measure.
So collaboration was key again. He wasn't trying to figure it all out in isolation.
Not at all. That willingness to ask, to lean on others' expertise, seems crucial to how he moved forward and confirmed his findings.
Did the experiments reveal anything else unexpected, beyond just confirming the gap?
They did, actually. Later, more refined experiments showed these little wiggles in the measurements, specifically when looking at the derivative of the current voltage curve. That's Figure 12.
Wiggles. What were the wiggles?
The wiggles turned out to be related to phonons.
Phonons, like sound vibrations in the metal lattice.
Exactly. Tiny vibrations of the atoms.
Yeah.
It turns out these phonons are deeply involved in how electrons pair up in the BCS theory. Seeing those wiggles meant Giaever was actually probing subtle details of this electron-phonon interaction.
Wow. So he wasn't just seeing the gap, he was seeing how the superconductivity worked on a deeper level.
Pretty much. He said those experiments, seeing those wiggles predicted by theory, were what made him feel like a real physicist for the first time, like he was really seeing inside the phenomenon.
Incredible. It's almost like he stumbled into confirming multiple layers of this complex theory. But speaking of stumbling, there was something else he observed, wasn't there? Something he didn't initially realize the importance of.
Ah, yes. The missed Nobel, you could almost call it, though he didn't see it that way. This involves another brilliant physicist, Brian Josephson.
Okay, Josephson.
Yeah.
What did he predict?
In 1962, Josephson, who was very young at the time, made this astonishing prediction. If you have two superconductors separated by a thin insulator, like Giaever's setup, you could get a supercurrent flowing across the barrier with zero voltage drop.
Zero voltage, a current with no resistance through the insulator.
Exactly. The DC Josephson effect. Mind-bending stuff.
Dan Giaever.
Here's the amazing part. Giaever and his colleague Carl Magriel had actually seen this effect in their very first paper on tunneling between superconductors. It's right there in their figure 13.
They saw the zero voltage current.
They saw it, and they saw that it was sensitive to magnetic fields, which is another hallmark of the Josephson effect. But they completely misinterpreted it.
What did they think it was?
They just assumed it was tiny metallic shorts, little imperfections or pinholes in their oxide layer directly connecting the superconductors, just an experimental flaw.
Oh, wow. They saw it but dismissed it.
Yeah. Giaever himself was incredibly candid about it later. He said he was just too simple-minded at the time to grasp the physics. He saw the data, but didn't understand its profound theoretical significance.
Did he regret missing it? Missing another Nobel?
He always said no, genuinely, because, as he put it, he truly didn't understand it back then. It wasn't just about seeing it, it was about connecting it to the deeper quantum mechanics, which Josephson did. It's a really humble perspective.
That really highlights something profound about discovery, doesn't it? Observation isn't always enough. You need the framework, the understanding, to see what you're really looking at.
Absolutely. It shows that interplay between experiment and theory. Sometimes experiment leads, sometimes theory leads. Here, Josephson's theoretical insight was needed to make sense of an observation that was already technically made.
So looking back at his whole story, from nearly failing physics to these incredible discoveries and even the missed one, what were Giaever's big takeaways about how science gets done?
He often emphasized that the path is seldom direct. It wasn't a neat linear progression for him at all.
Clearly not.
And he had this interesting idea about newcomers having an advantage.
How so?
He thought their ignorance, essentially not knowing all the reasons why something shouldn't work or isn't worth trying according to established wisdom, could actually be a benefit.
Huh. So not being burdened by dogma lets you try crazy things.
Kind of, yeah. You might wander down paths an expert would dismiss, and sometimes those paths lead somewhere unexpected and important. It's a vote for the beginner's mind, maybe?
And clearly he didn't do it alone.
Oh, absolutely not. He constantly stressed how vital collaboration was. Getting advice, getting help from experts, people sharing equipment like Israel Jacobs did.
Right.
He felt incredibly lucky to be at GE, the right place at the right time, surrounded by supportive colleagues, so many friends, as he put it, who helped him selflessly.
It sounds like a really special environment.
It does, and it led him to a strong conviction about funding research.
Which
That society should simply pay more people to do pure, fundamental research. Just explore, follow curiosity, without necessarily having an immediate practical application in mind.
because that's where the unexpected breakthroughs often come from.
That was his firm belief, based on his own experience. The tunneling work, the energy gap stuff, it was fundamental physics. The applications, like insensitive magnetic field detectors, or even potentially quantum computing down the line, weren't the initial drivers.
It's a powerful message. So, reflecting on all this, Giaever's journey, the near failures, the breakthroughs, the missed discovery, the importance of ignorance and collaboration, it leaves us with a thought, doesn't it?
It really does.
For you listening, how might your own ignorance, maybe that beginner's perspective in some area, actually be an advantage? Could it open doors in your work, your field, especially if you combine it with seeking out help and working with others? What might you discover if you didn't assume you already knew what was impossible?